All right, gang, new unit. Shh. Unit 5. Integrals. Okay. Differential calculus, which we've been talking about for a while, is one of the great branches of calculus. Integral calculus is the other. 5.1, antiderivatives. Okay, we're going to be talking about reversing differentiation. I think this is new to some of you, if not many of you. Okay? So we finally got past the domains of your knowledge, some of you. We're going to be talking about reversing differentiation. We're going to be talking about general and particular antiderivatives. We'll be talking about a few examples that will be familiar but backward. And we'll talk about the rest when we get there. Okay. All right, so here we go. Given a functional relationship between two variable quantities, something looks like this. I love this line. Okay, so given something like that, that guy's the independent variable or the input, that guy's the dependent variable or the output. Okay, the derivative, that guy, or written like that. Okay, that tells us the instantaneous rate of change. Instantaneous rate of change of the output with respect to the input. Okay, we're well familiar with that by now. We've spent the last 2 units talking about derivatives. So now, can we undo it? Okay? So in differentiation, what do? We stick a function into the differentiation machine, and we get out the derivative function. And the question is, can we go the other way? Okay? So the question now is, now, given the rate of change over time, given the rate of change, can we find or recover the original functional relationship? Okay? So can we go backward? For instance, if we know an object's velocity over time, can we find its position? Okay? If we know the flow rate of liquid out of a tank, can we find how much is left in the tank? Okay? So we'll start with the simplest possible example. Simplest possible example. Okay, so if I tell you that the derivative is 0 everywhere, what is f? Excellent, good. Very, very good. Okay? So this, if you want to think about it this way, this guy tells you that your graph is flat. The graph of f is flat, perfectly horizontal everywhere. Okay? Okay, that's what that tells you. And so any constant function will do it. Okay? Excellent. F can be any constant function. Okay, again, I'll just write this. This tells you graph of f is flat, perfectly horizontal perfectly perfectly flat everywhere, so f can be any constant function. Okay? Or in other words, for all x, f takes the value of that constant, and c is an arbitrary constant. It can take any fixed value. Okay? So any of these guys will work. Okay, that guy will work, that guy, or anything in between. Any of those guys will work, okay? And if you have to check, you would check that the derivative of a constant is indeed 0. Good. Okay? All right. Does that make sense? All right, so what we were looking for there was a function whose derivative is the 0 function. Okay? We were doing the opposite of differentiation. We were doing anti-differentiation. And we were looking for what's called the antiderivative, or an antiderivative, of the 0 function. Okay? All right. So again, we asked, what function has as its derivative the 0 function? And the answer was that any constant function is an antiderivative of the 0 function, which is what that says. So function f is called an antiderivative of function little f if big F's derivative is identical to little f. If you don't want to write that, write this. F is the antiderivative, or an antiderivative, of little f. That's the same as saying that little f is the derivative of big F. Okay? So we're going backward. Okay, so again, a function big F is called an antiderivative of a function little f if the derivative of big F is little f. The general antiderivative of a function f describes the family of antiderivatives of f. Okay? So, again, what were we looking for here? We were looking for functions that had this as their derivative. We were looking for the antiderivatives of the 0 function. Any constant function is an antiderivative of the 0 function, and the collection of all constant functions, the family of all constant functions, is the general antiderivative of the 0 function. Okay? So for this example, we said any constant function is an antiderivative of the 0 function, and the family of all constant functions is the general antiderivative, essentially. Okay. Especially if this is new, please tell me if you have questions. Okay, good. All right. When we differentiate, we take a function, okay, and we spit out another function, the unique derivative function. When we anti-differentiate, we take in a function, and we spit out an entire family, an infinitely large family of antiderivatives, okay? So the reverse process is a bit different than differentiation. Okay, so let's look at that example again. The derivative told us the shape of the graph, okay? So point, that's another point, here's another point. Okay. The derivative of f tells us the slope of f at every x value. Okay? And therefore reveals the shape of the graph. Okay, the derivative of f tells us the shape of the graph of f. Okay, hence lecture 4.7, where all we talked about was shapes of graphs and what the derivative can tell us. But the derivative cannot tell us the graph's vertical position. Okay, the derivative tells us the shape of the graph, but it cannot tell us where the graph is situated vertically. Okay, again, we could find out from this that we had a constant function, that the graph was flat everywhere, but we couldn't tell where it was vertically. Okay? And this makes sense, because adding a constant to a function doesn't change its derivative. Adding a constant to a function doesn't affect its derivative. Okay? The derivative of a function plus a constant is just the derivative of the original function. Okay? So someone tells you the derivative, you can't tell which function it is up to an arbitrary constant. Okay? So you can't tell the arbitrary constant, is what I'm saying. Questions about this? Okay. Okay. So two functions that differ by a constant have the same derivative, so you can't distinguish between them just knowing the derivative. Okay. In fact, once you know one antiderivative, okay, so once you have, let's say, the zero constant function, okay, then you can get all the others, you can get the general antiderivative by just vertically shifting that guy, okay? So in fact, the general antiderivative of a function f is equal to any particular one plus an arbitrary constant. Okay, and that's what that says. If you've got an antiderivative, then you can get the general antiderivative by just shifting vertically, okay? By an arbitrary amount. Okay? All the functions with a particular derivative are obtained by finding one function that has that derivative and then adding an arbitrary constant. Okay? Out of one particular solution, we get many. And if you want to prove this, usually that's done with the mean value theorem, which we don't talk about. Okay. Example. Example. Okay, given little f Good. Find its general antiderivative, which we usually denote with the capital letter. Okay. All right, so we already talked about this one. Okay. The zero constant function. Its general antiderivative is this, okay, where c is an arbitrary constant. Okay, so that looks like this, and that looks like this, 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 and everything like that. Okay? All right. Slightly more interesting. What's the antiderivative of 1, folks? What has derivative 1? X. Excellent. So, that's a particular antiderivative, okay, is x, because the derivative of x is 1. So you just write that and you add an arbitrary constant and you're finished. Okay? Because what? Because x is an antiderivative, x plus 1 is an antiderivative, x minus pi is an antiderivative, anything like that is an antiderivative of 1. Okay? All those guys have the same derivative, 1. And indeed, only those guys have derivative 1. Everywhere. Okay? So what does this guy look like? Looks like that. Okay, what does that family look like? Looks like that. Okay, anything with slope 1 everywhere. One more. Okay, what has derivative x? Okay, so think about the power rule. Okay. Okay, think about the power rule. If you take a power function and you take its derivative, what happens? The exponent drops by 1. Okay? So to wind up at x to the 1, you want to take the derivative of something that looks like x to the 2. Yes?
Would it be 1/2 a? Or
Yeah, it'd be 1/2, yeah.
X.
To the 2?
Yeah.
Yes, good. Excellent. Okay, good. Yeah? Okay, so here you got x to the 1, okay? If you take the derivative of 1 exponent higher, so x to the 2, then you'll get something that looks a bit like x to the 1, okay? So that's how you kind of think about this. We're almost there, folks. Okay, so let's try x squared. Okay, but if we take its derivative, we wind up with 2x. Okay? So fix it. Okay, get rid of that 2 by multiplying by 1/2. And then you wind up with x. Okay? So use the power rule. You know you got to go up 1 in the exponent, okay? So that when you take the derivative, you go down 1, back down to x to the 1. Okay? So you try x squared. You see that you wind up with 2x once you take the derivative. So let's correct for that 2. Multiply by 1/2, and you wind up with x as the derivative. So an antiderivative of x is 1/2 x squared. Okay, that's a particular antiderivative. To get the general or all antiderivatives, you add an arbitrary constant. Okay? And that's that. So this looks like this, sort of. This looks like this. And this family, easy. Okay, good? Make sense? Okay, team. I've office hours today, and if I don't see you there, I'll see you on Friday. Thank you. All right, gang, we started talking about antiderivatives, which is our first subject in integral calculus. What did we talk about? We said, can we reverse differentiation? And then we started by trying to reverse the zero function. And then we saw that the derivative can tell us the shape of a graph, but not its sort of vertical position. Okay, when we talked about antiderivatives, We talk about general and particular antiderivatives, and you can get the general one by adding an arbitrary constant to any particular one. And then we did a few examples, and then we'll continue from there. At any point, if you have a question, speak up. Given function, I'm going to repeat stuff from last time, so if you've written it, you don't have to write it again. Find the general antiderivative big F. Okay. We start with a function that's 0 everywhere, and we said that the general antiderivative was the family of constant functions. Okay? And at any point, you can check an antiderivative, take its derivative, and see that you get the thing over here. Okay? And if you don't, you've made a mistake. Either in going that way or going that way. Okay? So you can always check an antiderivative by taking the derivative. Okay. The constant function 1. A particular antiderivative was x, and we had an arbitrary constant to get the whole family. For x, we had to do a tiny bit of work. Very Macbethy there. Party, party.
Are you okay?
Me or the computer? Okay, good. Okay, so we talked about trying to find the antiderivative of x, and we said the power rule tells us that if we take the derivative of a power function, the exponent drops by 1. So to get here, let's jack up the exponent by 1 to x squared. Okay, and we said that if we took, this is all from last time, if we take the derivative of x squared, we wind up with 2x, not x. We wanted x, so we add a sort of correcting factor of a half. Okay, that cancels the 2, and we get what we wanted. Okay, so particular antiderivative of x is 1/2 x squared, and we add an arbitrary constant to get the whole family. Okay? Questions, let me know. Okay. For the record, the motto of the United States is "E pluribus unum," which means "out of many, one." So these are my attempts at references to that. Okay. That's the power rule, which we just used. Okay, and we can reverse the power rule in general. Okay, and there's the general reverse of the power rule. So what we just did here for general n, okay, or for general exponent a. Okay, so for any constant exponent that's not -1, the general antiderivative of x to the a is that. Okay, so you crank up the exponent by 1 and then divide by that new exponent. Okay, so that's just that. Okay, so you can reverse the power rule in general. And why are we doing it in reverse? Because it's anti-differentiation. Okay, so if you want to get x to the a as your derivative, you say, well, we got to start with something that looks like x to the a plus 1. Okay, so then when we take the derivative, the exponent will drop by 1. But this guy's derivative is a plus 1 times x to the a. Okay, so again, to get x to the a, we have to add this, or we have to multiply by this correcting factor. And that cancel, and we get x to the a. So that's what that is. Okay? So when you take the derivative of a power function, the exponent drops by 1. When you take the antiderivative, you crank up the exponent by 1. And to get the general antiderivative, you add an arbitrary constant. Every differentiation rule has an anti-differentiation analog. Okay? You just get it by reading the table backward. And in fact, the last thing we're going to do in this course has to do with reversing the chain rule. Which is probably nicer than you probably think it is. Okay. Quick example of applying this thing. Okay, the antiderivative, general antiderivative of x squared, crank up the exponent by 1, and divide by the new exponent. And add c. So 1/3 x cubed plus c. Simple as that, okay? So practice these things, otherwise you might make mistakes because we're learning two things that are opposites of each other. Just one more example. One over the 5th root of x, just to show you that these things count as power functions. Okay, you can rewrite this as x to the minus 1/5. And then you do the same deal. Okay, crank up the exponent by 1, so the exponent becomes 4 over 5. Divide by that new exponent, or multiply by 5 over 4, and add the arbitrary constant, and that's it. Okay? And here's a picture for that, in case you're interested. Okay, the red guy's the derivative, the black guy's the antiderivative. And you can do your usual checks, right? The derivative is negative, this guy's decreasing. The derivative is positive, this guy's increasing. The derivative is not defined here at all. And you do wind up with a cusp here. It's a local minimum, because the function's continuous, and the derivative went from negative to positive. In fact, a global minimum. Okay? And you can get all the antiderivatives by just shifting this guy up and down, right? The black guy up and down vertically, okay? Which is equivalent to adding an arbitrary constant. Fun fact, you don't need to know this. Fun fact, because the derivative is not defined here, actually, you can get more antiderivatives than just shifting the whole thing up and down. You can actually take the two branches and move them up and down independently. So it's all crazy. You don't need to know that. What you do need to know is that to get antiderivatives, general antiderivatives, or the general antiderivative, you shift up and down, okay? Any particular antiderivative. Does that make sense? Okay, so the black guy shifted up and down any amount will have derivative the red guy. Okay, you'll notice we said that that reverse power rule thing does not work for a equals minus 1. Yeah? So, what about x to the minus 1? All right, people, what has derivative x to the minus 1? Yeah? Awesome. Okay, so, now then, let's start here. Okay, so we said that ln x has derivative 1 over x. But ln's only defined for positive x. Okay, so I wrote that. And then I showed you this picture. Okay, and everything made sense. But in tutorial I said that we're missing something, okay? Because 1 over x has domain everything but 0. So what happened to all the negative guys? Okay? So what's the missing piece? And we said that if you look at ln minus x, and you take the derivative of that, ln minus x is defined for all negative x, and if you take the derivative using the chain rule, you get 1 over minus x times derivative of minus x, which is minus 1. Would you look at that? It's 1 over x as well, okay? Except for negative x, because this guy's only defined for negative x. Okay?
So essentially you're applying everything opposite of like the operation wise.
What we're trying to find right now is something that has that derivative.
Okay.
Yeah? Yeah, so we're doing this in reverse. I'm just trying to figure out what the thing is. Yeah, we're doing everything in reverse. So again, the problem here was that ln doesn't cover the entire region where 1 over x is differentiable. So we're missing a piece, and that's the missing piece. Okay? Okay, so, good. So in general, you know what, I'm already like that, already like this. So when we have 1 over x, we can write the general antiderivative ln absolute value of x plus c. Okay, when x is positive, we get this guy, okay, and we get 1 over x for the positives. When x is negative, ln absolute x is ln negative x, and we get derivative 1 over x for the negatives. If you have questions about that, say now or later. And I did this in tutorial as well, just for the record. Okay, so there you go. We're saying that this guy, okay, and notice this guy is around everywhere but 0 now, okay, so it can be a legitimate antiderivative of this guy, which is defined everywhere but 0, and is differentiable everywhere but 0. And there you go, that guy's the antiderivative, and if you want all antiderivatives, you just shift this guy up and down. Okay, you shift the black guy up and down. Questions about this? Again, we were missing a piece, we looked for the other piece, and the other piece was this, and we can sort of talk about both these guys at once by talking about ln absolute x.
But like, how do we like find the other piece? Like, do we like apply the reverse of the operations? I don't really.
This is something someone usually tells you rather than something I ask you, right?
Yeah.
Right.
Like when like questions get harder, you know, like me.
Okay. Usually, what you have to do is you have to think what had this derivative. So you have to look in your bank of experience and think what had this derivative, right? So for 1 over x, you go, oh yeah, ln gave me 1 over x there, right? Is that fair? So we're trying to reverse something. Usually, you look back in the stuff that you've seen. What took me to 1 over
so
x?
It's just a bunch of like memory. And, like,
No, learning. Practice is the right. Yeah.
okay.
You've done it this way. Yeah, you could do it all from scratch. So it's not really memory, but you don't want to do it from scratch, right?
Okay.
Yeah. And the missing piece just comes from realizing that this probably has the same-ish kind of form. If I look at something like this, chain rule does give me that. And incidentally, you don't need to know this, but because this guy, again, the derivative is not defined as 0, technically, we can also get antiderivatives by moving these branches around independently. But you don't need to know that. All you need to know is that you can get all the antiderivatives by shifting the black guy up and down as far as you want. Any questions? Okay. All right. That sinister laugh was because I looked at the time. All right, what is the antiderivative of this thing? What's it going to look like? Roughly.
3x or ln 3.
Oh, good. Good. Okay, so you could say, okay, well, it's an exponential. It's the derivative of an exponential is some constant multiple of the exponential. So let's try this as our first guess. If we did try that, she's absolutely right. If you did try this, okay, you'd get ln 3 times 3 to the x. Okay, so as usual, correcting factor. You get what you want, okay? And with practice, you won't even have to do this correcting factor thing. It'll happen in your head, and it'll just turn up on the paper. Okay? Something's unclear, please say. Nothing new here, okay? We talked about how the derivative of a sum is the sum of the derivatives, and how the derivative of a constant multiple is a constant multiple of the derivative. This is just that backward, okay? So anti-differentiation is nice. You can pull out constants, and you can break up sums and differences. That's all that says, okay? So you don't have to write that whole thing, you can just write that. Here's an example. Again, nothing new. It's what you've done in reverse, and it's just a familiar fact. It's something that keeps happening, and it's a nice thing. You can pull out constants and break up sums. Okay, and we're going to do that here. Okay, so we want the general antiderivative of this thing. or let's say we want an antiderivative of this thing. So we break up the sum, we look at each piece separately, and we pull out the constant, so all we have to look at is x squared. We know an antiderivative of x squared is 1/3 x cubed, okay? Okay, so for that first piece, okay, we know an antiderivative of x squared is 1/3 x cubed. Okay, we can multiply that by 5 because of that rule. Then we look at the next piece. What has derivative cosine? Sine. So the answer is just plus 2 sine x. Plus an arbitrary constant. Okay? And if you want to check that, what do? You take the derivative. And then if you don't get this, you've got a problem. Again, break up the sum, pull out the constant, look at this guy, write its antiderivative, look at this guy, write its antiderivative, and then put everything together and add a c on the end. And that's all it is. Okay. All right. Okay, we're going to talk about setting the constants, because we've got this annoying arbitrary constant everywhere. Out of many, one. Okay, so I asked at one point, if we know an object's velocity over time, can we get its position? And yeah, if we know where we started, okay? Again, if we know the velocity profile, we can get the position profile if we know where we started. And that should make sense, okay? If someone just tells you how fast their car was going over time, you wouldn't know where they were unless you knew where they started from. Okay? Or some equivalent piece of information. Okay, so more generally, if we're given the derivative of a function, okay, we can anti-differentiate to get the function up to an arbitrary constant or a vertical shift. If we're additionally given a point on the graph, then we can fix the constant, okay, and that lets us fix one particular antiderivative. We'll do an example in a second, okay? Okay, let's do an example. Hopefully that'll make sense. Example. If the derivative of big F is sine x over 2, and we know that f takes the value 1 at 2 pi, good. Guess what? Find f. Okay? So we're given the derivative, we want the function itself. What do? We anti-differentiate. So, what will give us sine x over 2? If you know already, shout. I'll take that as we don't know. Okay? What gives you sine when you take the derivative? Something like cos. Okay, so if we try cos x over 2, because we want to get x over 2 in there. Okay, if I take the derivative of this, what happens to me? Quite obviously, you need to know derivatives to be able to do any of this, right? Okay, chain rule. The derivative of cos is minus sine. So minus sine applied at what it sees, x over 2, times the derivative of the inside, which is 1/2. That's not quite what we want. What do when we've got something that's not quite what we want? We multiply by a correcting factor. If we correct by minus 2, multiply by minus 2, that fixes everything, and we get what we wanted. Okay? Again, that might happen in your head with a bit of practice. Okay, so what does that tell you? It tells you the antiderivative was this puppy plus c. So the general antiderivative is minus 2 cos x over 2 plus c. Again, take the derivative, make sure you get the right answer. Okay, and that is the general solution. Okay? What? The red guy is the derivative. All the dashed black guys are possible antiderivatives, right? We don't have just one solution, and no one's happy with that, right? You want one solution. Okay, but because that arbitrary constant, we don't know where this thing is up to a vertical shift, okay? And I've not even shown you all vertical shifts, that would cover the whole plane. We've got all those possible solutions. Which one is the right one? So we pick it out because we've got this additional information here, and that's what I was talking about. When you have additional information, like where did your car start, then you can fix the solution. So that's what we'll do. Okay, we were told this, so we'll use the fact that the function took value 1 at 2 pi. Okay, let's do that. So 1 is equal to minus 2 cos 2 pi over 2 plus c. Okay? 2 pi over 2 is pi. What's cos of pi? Minus 1. Minus 2 minus 1 plus c. Okay? That's 2. 1 minus 2 is minus 1, so c is minus 1. There you go. You fixed your c with that additional piece of information. And that's your particular solution. And that's it. That's what you're asked to find. Okay? You're asked to find the function that satisfies both of those things. And that's what you did. So you had the whole damn family of infinitely many antiderivatives. And with that additional point, hey, you could fix that one guy that was the right answer. Out of many, you picked one. Okay? Excellent. If you want to check your answer, what do? You take the derivative, make sure you get the right derivative, and you plug in 2 pi and make sure you get the right value out. Okay? Incidentally, you may remember when we were talking about differential equations, and essentially this anti-differentiation thing is dealing with very, very lightweight differential equations. When we talked about differential equations, we said that sometimes you need additional information to pin down a particular solution, right? Or in fact, always you need that. So when we talked about sort of the exponential growth law, okay, when we talked about the differential equation, we said that there are infinitely many solutions. To pin down one solution, you need to know your initial population or something like that. Okay? So this is that same kind of thing. If you're given a piece of information like that, you get to pin down a particular solution. All right. This guy's continuous, so look at this. If this guy changes sign, we get a local extremum. Okay? If the derivative changes direction, we get an inflection point. Everything makes sense. Okay? All right. Almost there. Higher order antiderivative. Okay, we're going to do a projectile motion example with no numbers at all to make you upset. Okay. Suppose an object is thrown from a height y0 above the ground with initial velocity v0 upward. Neglect air resistance. While airborne, the object's acceleration is constant and equal to g downward. Determine a function describing the object's height y above the ground at time t while airborne. Okay? If you've taken physics, you may have seen this equation that we're going to come up with. Okay, and if all the variables upset you, try this again with numbers. Okay, so what are we told? We're told that acceleration is 9.8 down. The object's height is measured above the ground, okay? So the up direction is positive. So the acceleration being downward means we should write it as negative. So again, acceleration is the second derivative of position. We get this, okay? Again, acceleration is constant downward and has magnitude g. Okay, that's acceleration. Again, check those directions. All right, well, we want to get velocity first, so let's get velocity. So we anti-differentiate. So let's get velocity. Velocity minus g, okay? An antiderivative would be minus gt. So minus gt plus a constant, let's call it c1, would be the general solution, okay? If I took the derivative of this, I get minus g, okay? Or if that doesn't make sense, the antiderivative of 1 and antiderivative of 1 is just t, and you can multiply by minus g to get minus gt, and then add the constant. Okay. Now you can impose the initial condition. Okay, I don't care if you call it that or not, you're just using the information you were given. And the information that was pertinent to velocity was that velocity initially was v naught upward, okay? And I said up was positive. So we're saying that the initial velocity is v naught. Okay, just plug it in. So v naught is equal to minus g times 0 plus c1. Hey, looky, looky. C1 just represents the initial velocity of the projectile. This is just initial velocity. We anti-differentiated once, and we got the velocity. We'll do it again to get the position. Okay, so we anti-differentiate again to get the position. Vertical position. Okay, be careful. Antiderivative of t is 1/2 t squared. Okay, so we're going to wind up with minus 1/2 gt squared. You can always pull out constants and break out sums, remember? Antiderivative of a constant is the constant times t. And again, you can always check this stuff by taking the derivative and making sure you get the thing that you thought you'd get. Again, plus a constant to get the general solution. Okay. Again, you had an initial condition. Impose the initial condition. Call it what you want. Additional information, whatever. Okay, and that was that you started at height y naught. Okay, so your initial height was y naught. Plug it in. Y naught is equal to minus 1/2 g0 squared plus v naught 0 plus c2. And look at that. Okay? Just write that right here. Okay, so it turned out that this constant actually meant something like the other one. This is just the initial position. That's it, okay? Anti-differentiate as many times as you need to, apply initial conditions or additional information, get a particular solution if it's possible. Okay, notice each time we anti-differentiated, we got a new constant added in, okay? That's a general rule. Okay, every time you anti-differentiate, you add a degree of freedom. And you need one more piece of information to describe the particular solution. So here we needed 2 pieces of information, initial velocity and initial height, to describe the particular solution. Okay. Right there, so as not to obstruct you. I could have instead specified I could have specified the velocity and the position at some other time other than 0, or I could have specified the values of y at 2 different times. Okay, so instead of telling you what the initial velocity was and the initial position was, I could have told you the velocity and position at another time, or I could have told you the values of the position at 2 different times. Okay? And if I'd done that, you would have gotten all the way down here, okay? And then you would have gotten 2 equations, one by plugging in the one value of y, one by plugging in the other value of y, and then you'd have to have solved that system of equations. You'd have had 2 equations, you'd have to solve that. Okay, does that make any sense? Okay? So if I tell you something like, what the initial position was and what the position was at time 1, okay? You plug that sort of stuff into this, and then you plug that guy into this, and you get 2 equations, and you have to solve them for the 2 constants. Okay? I can do that for you later if you want me to. Okay, all the stuff we just did, you can extend to more higher order antiderivatives. Okay, we just antidifferentiated twice. If someone had given you the jerk for some weird reason, you could have antidifferentiated 3 times. And also you can do this for non-constant acceleration. Okay? So this stuff all generalizes. Okay? You just take the antiderivative until you've got what you need, apply initial conditions, and get your solution. Any questions? Again, if you don't know what the heck I'm talking about over there or anything else, ask me. Okay?